introduction. Thanks for the invitation. Really glad to be here again. And let me wait for people coming in. Okay. So actually this talk is much more elementary than the title might suggest. I will not use any fancy terminology. Well, there are quiver moduli spaces. I'll just wait a little bit. Okay. For those who somehow know the subject, there are quiver moduli spaces in the background, but while I will avoid quivers, there are motivic Donaldson-Thomas invariants in the background, but I also will avoid them and try to keep things as elementary as possible and try to motivate everything. So so this is joint work with Alessandra Struck and Frédéric Chapoton from Strasbourg, Karen Martinez from Madrid, and there's an archive preprint from last month. So let me start by motivating everything with, if you're not into Kronecker moduli yet, by a linear algebra problem, a hard linear algebra problem. A linear algebra problem. Well, I guess this will be something we all can relate to, that this is maybe interesting in itself. It actually connects to physics. String theorists are interested in this linear algebra problem, but we will just motivate it by linear algebra. So let's work over the complex numbers and fix two finite dimensional complex vector spaces. So let V and W be finite dimensional complex vector spaces of dimensions D and E respectively. So let M be an integer, at least one. And now we consider M tuples of linear maps from V to W. Consider M tuples F1 to Fm of linear maps from V to W. And so here's the linear algebra problem. Classify them up to the natural notion of conjugacy or base change. So problem, classify them up to base change. And let me reformulate this as a group action, i.e. up to the GLV cross GLW action, which looks as follows. If you have G in GLV and H in GLW, then this acts on the tuple F1 to Fn by simultaneous base change. So HF1 G inverse, comma HFM. G inverse. Or you could choose a fixed basis and say we have an M tuple of rectangular matrices and we want to classify this M tuple of rectangular matrix, or this linear family of matrices, up to row and column operations. That's the matrix formulation for this problem. Okay, and so let's see if we can solve this problem. For m equals 1, we definitely can. We all know from first year linear algebra, of course, it's just one linear map up to row and column operations, and there are three discrete invariants, D, E, and the rank of the matrix. Three discrete invariants, D, E, and the rank of this map, F1. And that classifies everything up to the, well, there's an obvious restriction that the rank is something between 0 and the minimum of D and E, and that does the trick. So for m equals 2, classification is more subtle, but it was achieved by Kronecker in 1890. That's why they are called Kronecker moduli. And let me at least convince you that the problem of conjugation of a square matrix is somehow part of this classification problem. So in particular, we can look at the situation where V and W are the same vector space. And then we can say that the first map, F1, is the identity. F1 is the identity. And then, of course, we break the symmetry in our base change down to just conjugation by an element of GLV. So for the second matrix, we have the problem of conjugation of a square matrix. And so, for example, we can put the Jordan canonical form here. And this is somewhat part of the solution to this classification problem. OK, now to m greater or equal 3, and we have an unsolved linear algebra problem. There's just no solution. So there's no known classification. And let me show you where the problem is, at least, and attempt some kind of generic classification. Let's assume that this tuple of, well, let's work with m equals 3 and just assume that this tuple of triple of linear maps is in general position. And then I will show you a generic classification. And this will show you that the problem depends on many, many continuous parameters. So, depends on many continuous parameters. For example, again, let's assume that V and W are the same vector space. And let's proceed as in the m equals 2 case. So that's why I detailed this. So the first map, if it's in general position, we can assume it to be invertible. So we can transform it to the identity. This breaks the symmetry down to conjugation action of GLV. And what is the most general case for the conjugation action? A regular semi-simple element. So diagonalizable with pairwise different eigenvalues. So let's assume that the second matrix is diagonal matrix lambda 1 to, say, lambda d, where the lambda I are pairwise different. This breaks the symmetry group further down to the group of diagonal matrices and permutation matrices. Yeah? Because, well, these are complex numbers. We cannot fix an ordering. So we have to keep them arbitrary. So there's still the permutation action, permuting these. And so we're acting on the third matrix just with the torus, with the normalizer of the torus and permutation matrices. So what you can do then is the following. Well, we can assume that all the first off diagonal entries are non-zero, and we can normalize them to 1. And all other entries are then more or less arbitrary. Now the symmetry is completely broken because this choices of 1 here breaks all the torus symmetry. And what remains is an SD action. But an SD action means that you have finitely many of these normal form things which might be conjugate, but you have many continuous parameters. How many continuous parameters do we have? Well, we have d continuous parameters here, and here we have d squared minus d minus 1. So d plus d squared minus d minus 1 equals d squared plus 1 continuous parameters. But they are not independent of each other, because we made several genericity assumptions. There's the symmetric group action, so it's highly complicated. Yeah? And that is why there is no known classification. Yeah? So that is known in representation theory of algebras as a wild classification problem. Yeah? So with growing d, the number of continuous parameters which are involved in the classification grows quadratically with d. That's really, really bad news. Okay, so now what to do? I mean, we could just stop here and say there's no known classification, but we just want to do something. And we can at least study the continuous parameters and their dependencies qualitatively using algebraic geometry. That brings us to the second part of the talk, where I will now introduce the Kronecker moduli. Yeah, so the reaction on such a problem from algebraic geometry is to define moduli spaces encoding the continuous parameters. So just to do a reality check to m equals 1 and m equals 2. In the case m equals 1, we just have discrete invariants, so there are no moduli spaces. Well, there's no need for moduli space because there are no continuous parameters. In whatever way you define moduli spaces, they're either empty or single points. Yeah? In the second case, the Jordan-canonical form, well, the only continuous parameters you have are the eigenvalues of the matrix, so the moduli spaces will be something like affine spaces. Yeah? Affine spaces of dimension d, but now the dimension of the space is growing linearly instead of quadratically with the discrete parameters. Okay, so algebraic geometry wants to define moduli spaces, somehow encoding the continuous parameters and all the dependencies from each other, and that's what we will try to do. There are many, many different ways. I mean, what does space mean? Yeah? Space in algebraic geometry can mean many things. We will do the most basic one, quasi-projective algebraic varieties. So something which is explicitly embedded in some projective space by polynomial equalities and inequalities. And of course, you can think about algebraic spaces, moduli stacks, derived algebraic geometry, whatever. Yeah? But let's keep it basic and just define, well, actually manifolds. Complex algebraic manifolds. Okay, but, well, we can do this, we can define such a moduli space very naively. Namely, we take, let's first do the naive solution. The naive solution is to take the space of all possibilities, which means we take m tuples of linear maps from V to W. That encodes all our tuples of linear maps. And then we just mod out by this GLV cross GLW action. So just mod out by GLV cross GLW. That's why I formulated this as a group action. Yeah? So here you have a very nice algebraic group acting algebraically on very nice affine space, but the quotient is a mess. Yeah? So if you do this quotient topologically, so if you just take the quotient topology, you get an extremely bad non-Hausdorff space. So we definitely don't want to do this. So we have to take the quotient in a better way. One solution of algebraic geometry is to say, well, this is the solution due to Hilbert, well, we can always parameterize at least the closed orbits for this group action. And that's the best we can do algebraically. Bad news is there's only one closed orbit, namely the origin, the zero tuple of matrices, of linear maps. So that's not what we can do. So what we have to do is we have to well, what is the problem? The problem is, in taking this quotient space, some orbits are bigger than others. Yeah? So we have to throw away all the small orbits, like the zero tuple of linear maps. The zero tuple of linear maps is a single point which is also orbit. That's definitely very small. So we only want to keep the big orbits, and that is done somehow magically by Mumford's stability. So what we will now do is, so let me just say this has a very bad topology, and we ruled out some other possibilities, and now let me show you how to do it by introducing stability. The stability is some kind of genericity condition or condition of being in general position, which somehow automatically ensures that the orbits are big and that we can form this quotient as a nice topological space. All right, so I call such a tuple F1 to Fm stable if the following holds. Whenever I take a proper non-zero subspace of V, I can see how much this U spreads under all the linear maps. So what does it mean? Well, I apply all of these maps Fk of U, Fk to this U, and I take the sum over all of them. And I want this thing to be large, relatively large. Yeah, so the FKs, the linear maps, shouldn't be too equal or too parallel. They should somehow spread and be able to spread any subspace to something quite large. And quite large by Mumford means the dimension of this is strictly bigger than the fraction of the dimension of W by the dimension of V times the dimension of U. You don't have to make this up. Mumford's general GIT produces this condition for you automatically. Mumford has a general notion of stability. You work out what this means numerically by a Hilbert-Mumford criterion, and then you get to this condition automatically. You don't have to invent it. Okay, so theorem is, if we only consider the stable points, then we can form a quotient. So theorem. If we take the space of m tuples of linear maps, but we only take the stable tuples, this is maybe clear, this is just the stable locus, then we can just divide it by GLV cross GLW in the topological sense. So we just take the quotient topology on the set of orbits, and this has a natural structure of complex algebraic manifold. Is a complex algebraic manifold. Aha. For the topological considerations, which I will do in a minute, I would prefer this manifold to be compact because, well, compact manifolds, that's a theory that has a nice cohomological theory. They're not compact in general. They are compact if and only if, now that's a funny numerical condition, if and only if if and only if D and E are coprime. Manifold compact if and only if D and E are coprime. If you have ever encountered moduli spaces of vector bundles on curves, then you know such coprimality assumptions in the theory of vector bundles on curves. It's the coprimality of rank and degree of vector bundles, which ensures that you have moduli spaces which are compact manifolds. And that's similar. Compact. And of dimension, now I have to tell you about the dimension of this thing. The dimension of this thing is m times d times e minus d squared minus e squared plus 1 if non-empty. So this if non-empty sounds a bit suspicious, yeah? Hopefully we can say when the space is non-empty. We can, but that's another numerical thing which I want to add now. Okay. Okay.
Just notation. D and E are
still the dimensions of V and W. Yeah. Sometimes I really write dimension V, dimension W.
Yeah, but empty spaces compartment has any dimension. Yeah. Empty set.
Wonderful. Yeah, that's a very nice solution to this. Okay. Yeah. Okay. Here you see again the behavior, the quadratic behavior of the number of continuous parameters. Yeah, so this moduli space encodes the continuous parameters. The dimension is the number of continuous parameters. And this behaves, well, this is a quadratic form in D and E. Now there are two exceptions, namely the behavior of this quadratic form is totally different if m is 1 or 2 or m is greater or equal 3. Yeah, obviously. And because if m equals 2, then you can just write this as minus d minus e squared. Yeah, okay. So from now on, let me only consider the interesting case, namely that m is greater or equal 3. And let me now show you the condition when this is non-empty. This is non-empty if and only if, this dimension is something reasonable. So if and only if mdE minus d squared minus e squared is less than or equal 1. So if and only if the theoretical dimension is non-negative, then it is actually already non-empty and has this dimension.
Well, minus one.
Yes, let's make it. Yeah. plus 1 less than or equal 0. Greater or equal 0. Oh, sorry. Yes. Okay. Yeah. Completely mixed up style. Thanks. Yeah. If the theoretical dimension is actually non-negative. Yeah. Okay. For m equals greater or equal 3. So only for the interesting case. This is otherwise there are some oddities. All right. So, yeah, this is all rather nice. So that's now some of the story up to 1964, up to Mumford's book on geometric invariant theory. And there's one draw. I mean, the story looks absolutely nice. Now we have this moduli spaces. And now, of course, we can say solving this classification problem is now translated, at least the first approximation, to studying these moduli spaces. Studying these spaces in terms of algebraic geometry. I haven't given a name to them. They should have a name. And since this name is important, I will use the red chalk. So let me define this as just KDE, the Kronecker mod. So, and let me squeeze the theorem signifier in front. So KDE. I suppress the m in the notation because I want to keep the m fixed. Important thing is the numerical parameters d and e, the dimension of the spaces involved. This is the Kronecker moduli KDE. It's even easy to memorize. It's compact if d and e are coprime. For the things I want to do, namely for considering motivic generating series, I would really prefer to define motivic generating series of compact manifolds. These are not compact manifolds only for certain special d and e. That's the drawback, because I want to consider multiples of a fixed dE. And therefore I have to do something. Well, this is the only very short technical part of this. I have to consider another version of these moduli spaces, so-called framed moduli spaces. So in the theory of moduli spaces, that's quite a common phenomenon. You have some assumption on your numerical parameters, like coprimality, making the spaces nice, and otherwise the spaces are bad. I mean, okay, so this is in general non-compact. So, well, let's compactify it. Well, the only compactification which is known in general is singular. Yeah, by not parametrizing stable but semi-stable such tuples. But this is a singular compactification. Then we have some compact spaces, but they're highly singular, so this is also bad. So can we define moduli spaces which are both manifolds and compact? Yes, we can, but we have to ever so slightly modify the classification problem. So we have to cheat. We can define nice moduli spaces, but we have to cheat a little bit by modifying the problem. But the modification is really, really tiny. Consider not only these tuples f1 to fm, as before, but now also w. And w is just a vector in the vector space w. So this is just a single vector. These are all in linear maps. And now we consider not only these linear maps, but also this vector. And again, up to the GLV cross GLW action. Well, there's an obvious GLW action. You just move this vector W around. And now I consider a modification of the stability condition. Call it stable again. If, well, and now we can relax this condition a little bit. We can say that the dimension of the spreading out of any subspace should be greater or equal dimension W by dimension V times dimension U for all subspaces. And this should be strict whenever W is contained in here. And this simple modification surprisingly does the trick. Yeah? So I consider a modified problem. I keep this together with a so-called framing datum. And in our case, the framing datum is just a single vector, which we also move with the group action. And we can, in principle, relax our stability condition to semi-stability. But now we require that this is actually a strict inequality whenever W is contained in the spreading out of the images. And then the theorem is, now we get a compact manifold as the quotient. So now let me call this, here's the original. Now let me call this new moduli space KDE framed. That's the framing datum. And that's why I call it framed here. And now this is really, I take again the whole parameter space. I not only take m tuples of linear maps, but I also take W. I consider the stable tuples in here with respect to this new stability condition. And again, I mod out by GLV cross GLW. This always exists as compact algebraic manifold. Is a complex compact algebraic manifold. And the only thing I have to tell you more about this, I will not tell you about non-emptiness and dimension. It's all known, but we don't need it. I will only tell you about a little reality check. What happens in the case where our original space was good enough? Yeah? Namely in the coprime case. So in the coprime case, this is nothing else than a projective space bundle over the original space. So this actually maps to KDE and is a projective bundle. So the projectivization of a Zariski vector bundle if D and E are coprime. So that's the reality check. Yeah? So this space is not too far away from our honest moduli spaces in the case where the honest moduli space was good enough. Okay. So that was hopefully motivating. We have this linear algebra problem. We saw that it is hard, so we apply algebraic geometry to at least define moduli spaces. We had a first attempt at defining moduli spaces, which was almost good enough. We have to do something slightly different. And now what I want to do is I would like to study motivic generating series of this. And let me start with the simplest kind of motivic generating series. I will just keep DE fixed and then consider all multiples of D and E. This I can do with these spaces perfectly. Yeah? I should never consider multiples of a fixed DE here because then I don't have compact spaces anymore. But here I can take multiples of something fixed. And let's consider the most basic topological invariant, the Euler characteristic. And then we'll see we already get a very rich theory. And this we will start now. All right. So I think I can now, without problem, erase this motivation part. And now we'll consider motivic generating series of these framed moduli spaces, which is a bit technical, but this is where the good theorems are. But finally, at the end of the talk, I will come back to the honest moduli spaces, which I'm really interested in. That's some of the new theorems. So, 3 motivic generating series. And so let me fix, for this part, let me fix a slope. Let me fix a rational Q such that mu squared minus m mu plus 1 is strictly less than 0. So the slope should be the ratio of E by D, and then you will recognize this quadratic form again. Okay? And we write the slope as E by D for D and E coprime. Now this is strictly less than 0.
And one, but one is strange because you.
The 1 is gone just to make life easier, because there's one exceptional case for the real roots of the corresponding root system, which I don't want to consider. Okay, and now let's define the motivic generating series, F mu. That's a formal power series in T, and it is just the sum over, let me start with 1 plus, and then sum over all n greater equal 1. Let me just take the Euler characteristic of n times d, n times e, framed t to the n. Well, that's obviously a priori just a formal power series with constant term 1 and integer coefficients. Let me actually consider it in some field, namely the field of a rational coefficient Laurent series. And now comes the problematic part where I definitely need help from you. The following is, I write down a statement and you please tell me, is it a theorem, a claim, a conjecture, or an observation? Okay, so the theorem, definitely by Maxim and Jan, from about 2015, is that these F mu are algebraic series. So it's algebraic as a power series, as a formal power series. So Maxime, you told me a proof when walking from the restaurant here to IHES 3 years ago, but I think it's not published.
Because it's the product will be rational map, yeah?
I think it's published.
It's published, okay. Okay, then I will ask you about the
Algebraicity?
the algebraicity.
No,
Paper about algebraicity is not published.
it's not finished.
Okay,
Yeah.
so
Okay.
Yeah. But it was paper by Cordova, maybe. Yeah.
Let me call it a theorem. Okay, yeah? Let's optimistically call it a theorem, maybe not with written proof yet. Okay. One thing is to prove that they are algebraic, and the other is to actually write down a functional equation defining them. And I don't know if your proof actually shows, exhibits such an explicit functional equation. I will go into a slightly different direction. So let me just show you a theorem which I proved in 2011, just for the series F1, the so-called central slope. And F1, here's a functional equation for F1. F1 of t times 1 minus t F1 of t to the m minus 2 to the m equals 1. So that's the kind of functional equations or defining equations.
Actually, this morning we talked about this equation.
Sorry?
This morning when Carl Penson gave a talk, it was
This
Oh!
equation.
yeah.
Oh, great. Okay. So too bad my train was late. Yeah. Okay. So what I now want to do is, instead of trying to find an explicit functional equations for other slopes than 1, I will try to refine this. And what we considered is the very basic invariant of Euler characteristic. Now let's move from Euler characteristic to Betti numbers. Okay, let me refine this to Betti numbers. And this is something I was very interested in, because I wondered what a quantization of this functional equation would be. Yeah? Now passing from Euler characteristic to Betti numbers, it introduces an additional parameter, well, q, but I will call it v, quantum parameter v. So this will be a series dependent on v and t, and we will get a quantized version of this functional equation. I was really interested in how this looks like. So let me first introduce this. So let me define f mu of vt. And well, in the motivic sense, this v is minus square root of the Lefschetz motive. That's why I don't use the quantum parameter q, but v. Q would be like the Lefschetz motive, but this is a minus the square root of Lefschetz. This is 1 plus, again, sum over all n greater equal 1. And now sum over all integers Now I take the ith Betti number, and because these frame moduli spaces are compact manifolds, we can just take singular cohomology, nothing fancy. K, ND, NE framed. And now I use a slight twist. I take not v to the power I, but v to the power I minus the dimension of this guy here, t to the n. And okay, I'm cheating a little bit because there's not enough space. So I take the twist v to the I minus the dimension of this. So this here. Why do I do this? Well, I want to make Poincare duality manifest. Yeah? So these are compact, complex algebraic manifolds, so they have Poincare duality. And Poincare duality will be manifest, but this will be the automorphism exchanging V and V inverse. Yeah? And if I rescale the power of V here, then you see, well, if you consider zeroth cohomology, you get V to the minus the dimension. And if you consider top cohomology, which is twice the dimension, then you get the coefficient of V to the dimension. Yeah? And so you have, these are a palindromic version of the Poincare polynomial. So this is palindromic Poincare. Okay. And now I can already write down one of the main results of this new paper, which is an analog of this functional equation. And it is surprisingly quite a simple analog. Maybe one of the most obvious quantizations you can imagine. So the theorem now is, so this is a structure potent, Markus Reineke, that f1 is determined by the following functional equation. f1 equals the product over I from 1 to m, 1 minus v2, 2i minus m minus. In first approximation, ignore all powers of v. Yeah? Times t times product over j from 1 to m minus 2. f1 of v, 2i minus 2j minus 2t minus 1.
I think actually I knew this equation.
Sorry?
I think I knew this equation like 10 years ago.
Great. Okay, yeah. Okay. So I'm happy to confirm it. Okay, so let's again do a reality check and specialize v to 1 and see that we really specialize to this. Yeah? So what happens if we specialize v to 1? Well, we don't have to do any complicated limit process. If v goes to 1, this f1 v to something t just specializes to f1 1t. And then we have m minus 2 copies of that. So we have f1 1t to the m minus 2. We have this 1 minus t in front. Okay. Then we have an m-fold product of the inverses of this. So minus m. And this is f1 1t. And this is really exactly what we did there, just dividing by the right factor.
If all the powers of v are all odd or odd even at the same time, or not necessarily?
Yeah, I think so. Yeah.
Yes. The running parameters I and j, they only appear with the 2s. Yes, exactly. Yeah. So all motives are pure. Yeah. Okay, so that's the only thing I can do, this slope 1. Yeah? I would really love to do more slopes than 1, but that's the only thing I can do. But I can now, and the final part of the talk, I really have 10 minutes left. Wonderful. Yeah, okay, didn't expect this. Now we can go back to Kronecker moduli, to the original one. So back to the KDE. Namely, and this is quite tricky, I cannot explain the constructions which are behind this what you essentially do is, I mean, we have seen a relation between our we have seen a relation between our framed and non-framed moduli spaces. In the coprime case, the framed moduli space is just a projective space bundle over the unframed one. Now one can somehow generalize this relation by applying so-called reflection functors to all these moduli spaces. This is very subtle business, and one really has to be very careful with stability parameters, but at the end you get a connection between, so what is behind the thing, which I will explain now, is some mysterious relation between the k and n framed, and this is precisely our slope 1 case, and the k n minus 1 unframed. That came as a surprise to me, and the relation between these two is not directly geometric. It's just on the level of some series of motives. But there is a relation which I will now make explicit, but somehow that's behind the following. And this is interesting because, well, originally you would expect a relation between the framed and the unframed from NN, but NN is the worst case. Yeah, this is as far from coprimality of the two parameters as possible. But now there is a relation to NN minus 1, and these are coprime again. Wonderful. Okay, so let me define G1 of Vt as the same series, but now for this unframed thing. So 1 plus sum over n greater or equal 1, sum over all I, dimensions of the ith cohomology group of Kn n minus 1 unframed, and again v to the I minus the dimension of that thing, t to the I. And the theorem is that, well, essentially, yeah. T to the n, thanks. Yeah, of course. The I parameter is yeah, thanks. To the n. And the theorem is that this is related to f by a differential equation. That's, well, quite satisfying, yeah? So we have seen so far functional equations. Now we have finally a differential equation. That's not honestly true. It's a v difference equation, yeah? So I apply the v derivative, dv, of this G1 series. Let me recall what this v difference operator is. V difference operator applied to a series f is s of f of vt minus s f of v inverse t divided by v minus v inverse times t. It's a symmetric form of the usual q derivative. Yeah, the usual q derivative.
Function two variables, yeah. And you write here for function one. It's kind of v comma vt.
Yes. Thanks. Yeah. Okay. I tried not to erase this. No, but I better will. Yes. Yeah. Let's define the derivative of a two-variable as f of v vt minus s of v inverse t. Sorry, divided by v minus v inverse times t. So that's a symmetrized analog of the usual q derivative. And the q derivative, well, this v derivative of G1 is again something like a quantized power of f. Namely, it's t times product over I from 1 to m minus 1, f1 of v to the m minus 2I t. That's it. Okay, so that adds a algebraic difference equation, and let's also dequantize this, so specialize v to 1 again to see what it means. So if we specialize v to 1, then this operator just specializes to the usual derivative in the variable t. So it's d by dt of g1 1t, and this is then just power t times f1 of 1t to the power m minus 1. And with a little bit of thought from this information, you can also define the G1 completely by the specialized G1 by an ODE. And yeah, okay. As I said, the proof needs a relation between these two moduli spaces, which is really indirect and requires several steps. So I cannot tell you much about this. So I better just stop here. Thank you very much.
Questions?
Is G1 algebraic or not?
Huh. No, this I don't know. I don't know.
Is there an action of some nice algebra on the direct sum of cohomology of the moduli?
Oh, no, but in fact,
I somehow
in fact, you expect G1 has a series with integer coefficient, yeah?
yeah.
Then it will be algebraic. Then it will be algebraic. We have the general reasons here.
There are no reasons for.
No, then it will be algebraic.
It will be algebraic. I mean, in general, well, the integral of an algebraic series is not algebraic anymore.
Yeah, but
No,
you have algebraic. Yeah, it's kind of like, it's not algebraic. It will be reduced equation because it will be non-homogeneous equation. But section 1 in this series also has with integer coefficients. Yes, so definitely should be algebraic.
Okay, great. Okay, yeah. I mean, I just kind of write down a function equation. To your question, yes, I think I expect that one can categorify these all these functional equations and differential equations by considering a certain part of the coha, but yeah, by taking the direct sum of all cohomologies and acting on it with the coha, and hopefully then there is a structure which somehow automatically gives these functional equations. But I just don't know what it is. Yeah.
Coha is a shuffle algebra for Kronecker.
Yeah, but well, we only need the semi-stable part of the coha for this, say, for the central slope. So it's some strange quotient of the shuffle algebra. Yeah? To get the coha of only of the semi-stable locus, we take the full coha and mod out by certain explicit ideal, but which is very difficult to handle. So, yeah. But yes, I mean, I would expect something like this. Yeah.
Then, thanks, Markus.
Thanks.